In this lecture, we are going to prove uh, theorem 3, and also we shall derive time-independent Schrödinger equation from time-dependent Schrödinger equation. But before going into the theorem 3, we first discuss about the concept of eigenfunctions and basis vectors. If we have an operator A, and when it acts on an eigenfunction, it gives the eigenvalue an and the eigenfunction, and this we know that this is known as eigenvalue equation. If psi n, where say n equal to 1, 2, 3 up to capital N, where capital N may goes to infinity. Now if psi n is set of eigenfunctions, then these eigenfunctions can be considered to be a set of basis functions of a Hilbert space. We have not discussed about Hilbert space, but in a later chapter of this course, we shall describe about Hilbert space. Now, the if psi n is a set of basis vectors, then any state vector can be expanded in terms of the set of basis vectors. That means a general state vector psi can be expanded in terms of the basis functions. Now, properties of basis functions. The basis functions must be linearly independent. And the inner product of two basis functions can be written as which is delta mn, and this delta is known as Kronecker delta, and its value is 1 when m is equal to n, and it is 0 when m is not equal to n. This condition is known as orthonormality condition. It means if we take inner product of psi m with psi m, then it is delta mn, and this is equal, delta mm, and this is equal to 1. And if m is not equal to n, then this is this, and this is equal to 0. Now we are ready to state and prove our theorem 3. Okay, what is this theorem? This theorem says that if phi j, where j is equal to 1, 2, 3, dot, 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 are the eigenfunctions of the Hermitian operator A, that is A psi j equal to aj, not psi j, this is A phi j equal to aj phi j, then the expectation value of the physical observable capital A in the state psi is given by this is the theorem, and now we would like to prove this theorem. Since we are given Therefore, where dV is the volume element and the integration is over the whole space. Now we substitute this expansion of psi where we have used separate, different index for this summation, second summation, because here there is a product here, and that is why we will have to use two different indices for the summations. We bring these summations outside the integral sign, and also we bring the constants outside the integral sign, and then we are left with this. Now since we have this this eigenvalue equation, so just instead of j we have here index k here, but we can use that. And this is ak phi k. Now ak is the eigenvalue, so we can bring that is also outside the integral sign. And we are left with this integral, which is nothing but the inner product of phi j and phi k. And this is, we can write down this Kronecker delta, and by the help of this delta we can we can reduce these two sums into one. How? If k, if you consider this summation over k, if k equal to j, then only this will give you, delta jk equal to 1. Otherwise this delta will give you 0, so only one term will survive, and that is when k equal to j. So wherever we see k, we just put j, and which is nothing but modulus of cj, aj and modulus of j. Therefore the expectation value of a is this, and this proves our theorem. Okay, next we shall now derive the time independent Schrodinger equation. Okay, now we know from postulate 5 of quantum theory the time dependent Schrödinger equation as I squared del psi by del t is equal to minus square by 2m and del square psi plus v psi. Let us suppose this is equation number 1, where psi is the state function, v is the potential energy function, and m is the mass of the system. We have assumed here that the potential energy function is a function of position x only. Now, in this situation, we can apply the separation of variable technique. By assuming psi is a product of two wave function, one depending only on position and the other depending only on time. Now, substituting 2 into 1, okay, if we substitute psi is the product of phi and f in the equation 1, then we get now dividing both sides by phi and phi f, we get let us suppose this is equation 4. What we see in equation 4 is that the left hand side of the equation is a function of time only, and the right hand side is a function of position x only, and this is vector x. Thus, both sides must be a constant. Let this constant be capital E. This capital E will not depend on position x and will not depend on time t. Therefore, we can write equation 4 as two equations. Yes. A constant. Let us suppose this equation number 5. So from 5 we can write down so we get two equations. So let's say this is 6 and another one is this. Now from equation 7, if we multiply both sides by 5, equation 7 can be rewritten as okay. This equation is known as the time independent Schrodinger equation. Okay, so we have derived the time independent Schrodinger equation. You see, in this equation there is no time variable. Oh, that's the total solution of the, we can write down the total solution. Okay, this is a new okay, topic here. We should discuss about, you know, the stationary states. Solution of the time dependent Schrodinger equation and the stationary state. Um, from equation 6 in the 6, see this equation. This is actually the byproduct. This is the time dependent part of the Schrodinger equation. So from equation 6, or we can say from the time dependent part of the Schrodinger equation, we have I squared 1 by f df by dt equal to E, and from this equation we can write down this, because I square equal to minus 1, Now integrating, okay, this one this is logarithm of f base E is ln f. So if we differentiate it with respect to time, then it will be 1 by f df by dt. Okay, integrating with respect to t, we get ln f minus I e t by h squared plus there is a constant ln c. This is a constant of integration. From this equation we can you bring this constant on the left hand side, so we can write down this f by c. Okay, from this relation we have f by c equal to exponential minus I e t by h squared. This one we get from, if a to the power x equal to b, then x equal to logarithm of b base a. Yeah, we know this because ln means logarithm base e. Okay, but f is a function of time, so is c exponential minus I e t by h. Therefore, the general solution of the time dependent Schrodinger equation is, that is psi, function of position x and time t, and it is phi into f. So phi is c e to the power minus I e t by h squared into phi. This is the general solution of the time dependent Schrodinger equation. Now the probability density of finding the system in state psi at position x and at time t is, which is, we know, modulus of wave function squared. So if it is rho, then this is modulus of psi square. Usually modulus of psi square means psi star into psi. So if we take psi star of this, we take star means complex conjugate, then we'll have complex conjugate of C, and this one will be to the power plus IET by square and complex conjugate phi. So it will be C star to the power plus IET by h cut phi star, and this one is C e to the power minus IET by h cut, and this is phi of x, which is written as modulus of C square and modulus of phi of x square, because we have phi star and phi. So what we see from this equation is that the probability density does not depend on time. And this is equation number 9. Or we see from equation 9 that we see from the expression of the probability density rho that it does not depend on time t. And this kind of state for which the probability density is independent of time is known as the stationary state of the system. This type of state for which the probability density does not depend on time is known as the stationary state. That's what we see. We see that the solution of the time-dependent Schrodinger equation is nothing but the stationary state, and this has this happened because of the potential energy function. Since the potential energy function, we have assumed that it does not depend on time, and that is where we were able to separate the time-dependent Schrodinger equation into two independent equations by applying the separation of variable techniques. Okay, this is for today. In the next lecture, we shall consider a relation between probability density and probability current density, and we will find an equation relating these two quantities. And also we shall consider parity operators